This topic is covered very fast with the expectation that the video viewer can start, stop, fast forward, rewind, and pause at their leisure. Got Kirchhoff? A capacitor in a complex circuit. Here's an interesting twist on a fairly common textbook problem, which looks for the state of a circuit while a capacitor is in the middle of charging. This material will be presented in 5 sections. First, a quick review, then I'll define the initial conditions of the circuit in the beginning, then I'll define the final conditions of the circuit at the end, then I'll derive a time-dependent equation for the currents, and finally I'll confirm those equations against the final conditions. We are told that initially the capacitor in the circuit shown is uncharged, and at t equals 0 the switch is closed. The goal is to derive expressions for the currents through the R, 2R, and 3R resistors as a function of time. We can assume that R and C and the EMF are knowns, and in the interest of time, I'll just show the derivation for one of the 3 currents, and then just show the others without all the details. So the first task is to find the t equals 0 and final steady state where t goes to infinity, limiting cases. Next, the goal is to find expressions for the currents as a function of time. Before we begin, I want to provide a quick review to make sure we're all on the same page. So on this slide, I provide a bit of reference in case viewers have forgotten. In the top left, there are some basic resistor rules for resistors in series and parallel. I'll use this when we're finding initial and final conditions. On the right, I've got some basic capacitor rules that will find some purpose. And on the lower left, I have a few expressions of the Kirchhoff, junction, and loop laws. For the first part of the problem, we want to find the characteristics of the circuit just after the switch is connected when t equals 0. When this happens, the charge in the capacitor is 0, the voltage across the capacitor is 0, and the capacitor can essentially be ignored like it was just a straight section of wire. We can do some basic resistor calculations ignoring the capacitor for now. I'm going to define R1 as R, R2 as 2R, and R3 as 3R because I'm clever like that. And since this is practically chapter intro stuff, I'm going to move through this pretty quickly since I'm really just interested in the results. First, I can find the combined resistance of the 2 parallel resistors on the right, then the total resistance of the circuit initially. Knowing the EMF voltage for the circuit, I can get the maximum current for the circuit, which is also the current through R1. With current and resistance, I can get the voltage across R1 as 5/11ths of the original EMF voltage. Kirchhoff's loop law tells me that the voltage drop across the rest of the circuit has to just be the second part of the drop to the bottom, which is the other 6/11ths of the original EMF voltage. With voltage and resistance, I can get the current through R2 and R3, which Kirchhoff junction law says have to add up to the current through R1, which is true. So that's good. For the second part of the problem, we want to find the characteristics of the circuit at time t as t goes to infinity. When this happens, we see that the charge in the capacitor is maxed out, the voltage across the capacitor is maxed out, and the current through the capacitor is effectively 0. The capacitor now acts like a break in the circuit, like there's a hole. Now when we do the basic resistor calculations again, we can just ignore the far right branch completely. This means the circuit becomes like a trivial one-loop circuit. I can add the resistors to get the final steady-state resistance in the total circuit. And from this, I get the one and only current in the circuit. Now, try to remember these final current values. They are both 1/3 of the EMF over the resistance. 1/3 of the EMF over the resistance. Remember that, because we're going to compare that at the very end. And then, of course, the voltages across each resistor. Here's a side-by-side comparison of before versus after. We can see the voltage across the top R1 resistor drops from about 45% to 1/3, while the right side of the circuit increases from about 55% to up to 2/3, and without that far right resistor to help out, the total resistance in the circuit increases and the total current drops as expected. And now the fun part, finding how the currents in the circuit change with time. Okay, first off, we need to get these 3 base equations to use to solve for the 3 time-dependent currents. For the first equation, I will apply Kirchhoff's loop law to the left loop. Remember that the current will ride these wires like a roller coaster from the highest electrical potential to the lowest. Kirchhoff said that all those ups and downs should cancel out. So here's what that looks like in the left loop. The rest is just math. So I isolate our EMF to get our EMF in terms of I1 and I2 currents. Then I can take the derivative of everything. Note that the time derivative of EMF is just 0. So now I've got an equation for I1 in terms of I2, which I will call equation A. Next, I will apply the junction law to relate all 3 currents in a derivation equation that I will call equation B. Finally, I will apply Kirchhoff's loop law to the right loop. Remember, we're tracking all the drops and rises in potential, so they will cancel out. And here's the result of that thought process. Remember that time-dependent capacitor charge is the time-dependent current integrated over time. So I can put that in here, but I've got all my other stuff expressed as derivatives. So I'll take the derivative of everything and get this relationship between I2 and I3 that I'll call equation C. So there's my 3 equations. Let's do some mathing. I notice that equation A and equation B both equal the same thing, so I can set them equal to each other and then simplify. And eventually I get this simple relationship between I2 and I3, which I will call equation D. Now, if you're thinking, hey, didn't we have another one of those? You'd be right. It was probably equation C you were thinking of, so now I can substitute the equation D equivalency into equation C. And I get this equation, which only has I3 terms in it. Very exciting. And I can simplify that down, clean it up a little more, put all those derivatives on the left, boil it down so we can get ready for some integration, and I'm just about done. Maybe just a bit more so I can integrate both sides, and this is ready to integrate. Yeah, I said that. So I'm going to integrate the left from initial to steady current and integrate the right from initial to steady time. And here it's been integrated. So now I only need to raise the exponential to the power of both sides to get rid of that natural log. And here's a nice expression for some current as a function of time and the initial current, which I'll call equation E. If I only knew what that initial current was, oh wait! Yeah, here's the part where I pull that initial value into the process. Recall those initial conditions way back in part B, and that initial current was, for I3 was 2/11 EMF over R. So let's look at equation E again. There's equation E, and I can put that into there and plug that in, and we've got our first big answer, the current through the far right resistor as a function of time. Whew! Oh my gosh, that was exhausting. I could apply a similar process and find the expressions for I2, and then of course I1 is just the sum of I2 and I3. So what's left for me to do now? Oh yeah, that. Okay, let's see if these equations are consistent with the final values discovered earlier. Here's our 3 equations for our time-dependent current. We've got I1 and I2 and I3. And we need to note that as t goes to infinity, that exponential component in the equation goes to 0. So everything with a 0 attached to it vanishes. So let's look at the first one. Well, that's easy enough. I1 becomes 1/3 EMF over R, which is what I told you to remember back when we should check this. This one is correct. How about number 2? Number 2 is a little more complicated, but it comes out to the same answer, so that's a winner too. And remember that I3 just turned into nothing, so that's consistent. Yay! I like it when it all works out. How about a short animation? So what I did here is I took the circuit and I redrew the circuit in 3 dimensions, with the third dimension being the potential level of each portion of the circuit, because that's the way I visualize it. Okay, so as time advances, we can see the capacitor in the foreground charging up. We see the voltage increasing in that section of the circuit. Here, let's play it again so you can watch all 3 components again. I think this is really cool. It helps me visualize what's going on. Thank you for your kind attention.